In the field of data compression, you're usually trying to create a scheme that will suit the data you're trying to compress. For instance, if your goal is image compression, you might look at an image and notice that pixels that are close to each other tend to have similar colors. So maybe you try to leverage that in some way. If you're trying to compress text, on the other hand, you might make use of the fact that human language has a lot of repetition in it. In other words, you're trying to adapt your algorithm to the data. But bzip2 is a bit different, in the sense that it adapts the data to its algorithm. It first rearranges the input in a way that is reversible and that can amplify some relatively simple compression techniques. So we'll start with one of these simple compression techniques. It uses something called run length encoding, or RLE, which basically takes consecutive repeating symbols in the input and compresses them as a pair of the repeating symbol and the number of occurrences. You could imagine that on data that has many runs of repeating symbols, RLE by itself could be quite effective. It's easy to see, however, that on most data in the real world, this technique doesn't perform well. In fact, it will usually achieve expansion instead of compression. It's quite rare to see files that have many long runs of repeating bytes. This is why, before doing run length encoding, bzip2 applies something called the Burrows-Wheeler Transform, or BWT for short. The way this transformation works is that you create a matrix of all the circular shifts of your input. A circular shift is when you take the element on the first position and move it to the last position while shifting everything to the left. So after you generated all the shifts, you sort the rows alphabetically. Then you take the last column. Now run length encoding can compress this last column much better. Here's an example of applying the BWT on a quote from a Charles Dickens novel. I'll only show the final result since the full matrix would be too large to fit on screen. Notice how effective run length encoding would be now. But why does applying this seemingly arbitrary transformation help with compression? To understand this, imagine you're trying to compress English text, which contains a lot of instances of the word the. This means that there will be a lot of shifts that start with HE and end in T. These will get sorted together, and in the end, the output will have a region with a disproportional amount of T's intermingled with other characters that may precede HE in the English language, such as S. Now, an important question is, how can the decompressor reverse this transformation? How can it tell what the original sequence of symbols was? Because if all the decompressor gets is a scrambled set of symbols, and it cannot retrieve the original string, then that's useless. So let's go through an example to see how the entire matrix can be reconstructed starting from the last column. Now, there is one detail I left out, the fact that the compressor must also save the index of the row of the original piece of data. That's all. So we know the last column, and we also know the row we cared most about. From there, we can also figure out what the first column is. Because remember, the first column is always going to be the set of characters sorted into ascending order. So we can just take the last column, sort it, and then we have the first column. Now, if we look at the first row, we see that it starts with E, and it ends with P. But remember, we generated the rows using circular shifts. That means that there was a row that started with P and was followed by E. This means that P comes before E. In other words, E comes after P. And if V comes before I, then I comes after V. And we can continue to do this to get the second column. And following the same logic, we can reconstruct the entire matrix, really. And you can see, in this case, the original string was Viper. Now, you might still be a bit skeptical about this, After all, I cherry-picked this example where every character occurs only once. What happens when there are multiple occurrences of the same character? So let's look at another example. Again, we have the last column and the index of the original string, which means that we also have the first column. Now, let's try to apply the same algorithm as before. So A comes after E. Well, that's ambiguous because there are two E's. E comes after N. Okay, that's easy. There's only one N. E comes after L. Again, there's only one L. I comes after P. Well, there are three P's. L comes after P. Again, there are three P's. P also comes after P. So again, I have to know which P I'm talking about. I have to know the order in which to place I, L, and P. But it turns out that's actually not difficult to do at all. Remember that the matrix is sorted alphabetically, which means that I, L, and P must also be placed in alphabetical order. There's no ambiguity here. Same goes for the E's. There's an E followed by an A, and there's an E followed by a P. So you just write down A and P in alphabetical order. This way we got the second column, and we can fill out the rest of the matrix as well using the same logic. And now the word was pineapple. So is that it? Just Burrows-Wheeler and run length encoding? Not quite. There are two more stages. bzip2 also uses something called Huffman coding at the end of its encoding process. What Huffman coding does is take frequently appearing symbols and encode them in fewer bits than less frequently appearing symbols. Now, explaining how Huffman coding generates these optimal code lengths is a bit out of the scope of this video, but I'm going to link a good explanation in the description if you're interested. But what you do need to keep in mind, however, is that Huffman relies on there being a skewed distribution of symbols. If all symbols have the same probability, then Huffman cannot do anything for you. That's why bzip2 applies one more transformation after the Burrows-Wheeler transform to amplify the effectiveness of Huffman coding, and that is the move to front transform. To perform the move to front transform, we first make a numbered list of all the symbols that appear in the input, called a stack. Now, it is called a stack, but it's not really a stack in the traditional sense of the word. We won't be pushing anything on top of it. If anything, it's more like a queue. But either way, it's called a stack. Then, at every step, we grab a symbol from the input, find its position in the list, store that in the output, then move the symbol to the front of the list, and repeat the process. Notice how larger indices tend to be less common than the smaller ones. The move to front transform creates a certain bias, since a character that appeared recently is going to be close to the front of the list. And this is really good since the Burrows-Wheeler transform tends to group occurrences of the same character together. And this skewed distribution of small indices makes it really easy for Huffman to compress the data even more. By the way, the example you see on screen right now is the result of applying the Burrows-Wheeler transform on the phrase to be or not to be. You can see that the distribution of symbols is more biased after the move to front transform. It is hard to see the impact of this technique on such a small example, but you could imagine this is going to help a lot on a longer string.